everybody. Tonight I'll be presenting about my physics project, term 2, my final physics project. Right, moving on, we have the big question this term, which is why do visionary leaders adapt? And we have the focus question, which is how can humans analyze transformation based on physics concepts and law in a day-to-day life activity? And the two outcomes that are highlighted in this term's physics course, we have able to develop a forward-thinking design based on the understanding of Newton's law of motion, as well as able to analyze a daily life problem based on the principle of work, energy, and power. Right, so I'll be explaining Newton's laws first, the three Newton's laws of motion. So in this picture, clearly you can see that I'm kicking this guy towards the left. 4 forces on the right indicate the colors of the arrows for the free body diagram. So I'm connected to this guy. The friction, so in this picture I'm sliding towards the left, right? I'm sliding towards the left, and the guy is also moving towards the left. This mat makes it harder for us to move towards the left because we're rubbing against the mat. So that's the friction, it moves towards here. And we also have the gravity, which is pointing downwards for the both of us and everybody else in this picture. We also have natural force, the both of us pointing upwards, and applied force applied, where I apply force towards this man's midsection to push him towards the left and gain a point. Newton's third law is what I'm trying to highlight in this picture. So when a force is applied to an object, it'll be an equal and opposite reaction. So I've applied force to this guy, and the force is equal once I kick into this guy, and it has an opposite reaction. So even though I kick him to the left, I traveled backwards to the right because I apply force towards him, and there's an equal and opposite reaction. Moving on, we have the second picture where I took a picture with my brother in a forest in New Zealand. So what I'm trying to highlight is Newton's first law: an object won't move unless a force acts upon it. So clearly, me and my brother wouldn't be in the air if it weren't for us trying to recreate this photo. And we applied force towards the earth so that our bodies can move upwards. The natural force, of course, the both of us would be pointing upwards. The friction is the air friction around our heads and our bodies, making it harder for us to go up. We also have gravity, both of these two arrows pointing downwards because gravitational forces work like that. And then we also have applied force, where here you can see that Sultan, my brother, is pushing down towards my foot, so my foot goes down towards the ground. He applies force. Thirdly, we have the third image here where I'm trying to dunk a basketball, definitely not regulation size. 4 of the same forces as mentioned in the 2 previous images. We have the 4 forces. Okay, so the natural force of me is pointing upwards over here, and then I applied force towards the ground, which propels me into the air. We also have friction, the air friction, as the last image was evident. There's air friction around me and Sultan when we both jump into the air, so the friction goes down. We also have gravity pulling me down as well. Now for the last and fourth photo, I have me approximately give or take 4 or 5 years old, and my mass at the time was about 20 kilograms, and I was on a slide, pretty tall one at that, which is 5 meters off the ground here, you can see. So this is me, I'm at the top of the slide, and I choose to highlight 3 points here, A, B, and C, where I go down the slide. These are the calculations. So of course, by this sticky note you can see that I'm trying to explain the law of conservation of energy, which include the kinetic energy, potential energy, and mechanical energy of an object. 3 points I choose to highlight as per the image as per the diagram in the previous slide. And here my mass is 20 kilograms, my velocity at point A is 0 meters per second, the gravity of the earth is 10 meters per second squared if you round up, and the height of the slide is about 5 meters. So on point A, I won't be moving, right? So definitely my potential energy would be at its highest, as all the stored energy within me, it resides fully there. And to find the kinetic energy, we just plug in the values of this potential energy into the mechanical energy formula, which is PE plus KE. So kinetic energy equals mechanical energy minus potential energy, and mechanical energy will remain constant throughout this whole experience, I would say, because it stays at 1,000 joules. It doesn't decrease, nor will it increase at any point, because it's the sum of two of these energies. So because I'm not moving, obviously my kinetic energy would be 0 joules. Moving on to point B, I start accelerating. So the potential energy, I'd say I was at a height of 2.5 meters here, because it's the midpoint approximately. So 20 times 10 times 2.5, where it becomes 500 joules of potential energy down here. As I start to accelerate, I'll gain more and more kinetic energy, and I use the same method here, shown here, to find the kinetic energy, which is 500 joules. So 1,000 from the constant mechanical energy minus 500 joules of the potential energy, which is 500 joules. To find the speed, we just substitute. So 500 joules being the kinetic energy over here, then half times mass of myself, which is 20 kilograms, and the velocity squared. We have 500 equals 10 times velocity squared, 50 equals velocity squared. So yeah, which means the velocity here is about 7.07 meters a second. So I rounded up to 7.1 meters a second. On point C, I'll be traveling the fastest I am on this slide, so the potential energy would be 0, effectively. Then we also have the kinetic energy, which is, I use the same method over and over again. So 1,000 of the kinetic energy minus 0 of the potential energy, so it has 1,000 joules. Then to count the speed as well, same method as this one. 1,000 joules equals half times 20 times velocity squared, so 100 equals velocity squared, and velocity squared equals 10, just velocity equals 10 meters a second. I'll be traveling 10 meters a second on this bottom point. And as you can see, the mechanical energy remains constant, right? So there isn't the energy of this universe, it won't be destroyed, or it won't change at all, because all energy does is just changes forms. So for example, you take a light bulb, it turns electricity into light energy. You also have your hair dryer, where it turns electricity into heat energy. And in this case, all the mechanical, the potential energy up here turns into kinetic energy as I slide down the slide. And of course, the mechanical energy never changes, because that's the total energy I have throughout all this. That leads me, then we have the table over here, where I just display my data in a more effective manner. So you can see here the speed, 0 meters a second, the height, 5 meters at the highest point of the slide, and then the potential energy, because I'm not moving, 1,000 joules, kinetic energy 0 joules because I'm not moving, and mechanical energy remains constant towards during all this. That leads us to our conclusion, so in conclusion, we can see the laws of physics, the Newton's laws, or the laws of conservation of energy. They govern the known universe and how it works. We can't ignore the laws, because it is the very bedrock, or the very foundation of our world. Nothing would make sense without the laws of physics. So we really can't ignore those laws. For example, for an object to move, there must always be a force that moves it. For example, I have an eraser on my table. It remains on the table if I don't move it with any force, right? But if I snap my fingers, if I move it, push it with my fingers, then the eraser moves, right? It's because I applied force using my finger towards the eraser. So without that force, the eraser wouldn't move, which is a great example of Newton's first law, right? And that's That's all I have to say. Thank you for listening to my video, and I'll see you next time.